So today we're looking at the HoloMotion-1 technical report by Horizon Robotics, and we're just going to jump right in because this is a humanoid motion foundation model that actually achieves zero-shot whole body tracking.
Yeah, zero shot. It's huge.
Right, and they pull this off using three main pillars. First, there's a massive hybrid training corpus, over 2,000 hours, which heavily relies on video reconstructed in the wild motion. Second, they use a sparsely activated mixture of experts transformer, so a MoE, along with KV cache inference. And third, and this is the really wild part, they use a sequence-level PPO optimization strategy that speeds up training throughput by like 22 times.
Which is just an insane bottleneck to clear.
Exactly.
Yeah.
The final result is a 40% reduction in tracking error compared to state-of-the-art baselines like Sonic. And it transfers directly to a real Unitree G1 robot without any task-specific fine-tuning. So we are AI Paper Swap, where we summarize the latest AI and tech papers, and today we're breaking down how Horizon actually built this.
Yeah, and, to really understand the gravity of what they've done, especially if you're an ML engineer or a roboticist listening to this, you have to think about the latency budget.
Oh, the dreaded latency budget.
Right, because scaling humanoid control is fundamentally a much harsher engineering environment than, say, scaling large language models. With NLP, a few hundred milliseconds of inference latency is, well, it's just a slight pause before the text generates on your screen.
Right. The user maybe gets slightly annoyed, but nothing breaks.
Exactly. But in robotics, you are bound to incredibly strict real-time control loops. You're usually trying to hit something like a 50 hertz update rate.
So that's, what, 20 milliseconds?
Yeah, exactly, 20 milliseconds. If your massive sequence model misses that window to calculate the torques, the physical system diverges from the safe state, and the robot falls over.
It crashes into the concrete.
Right, and that's not even mentioning the sim-to-real gap, right?
Yeah.
The friction and the dynamics of a real floor almost never perfectly match the physics simulator where you trained the model.
Yeah, so HoloMotion-1 is basically attacking both of these massive problems at once. The data bottleneck and the compute bottleneck on the edge hardware.
Exactly, it's a dual breakthrough.
Because anyone who has tried to deploy a high-capacity transformer to embedded hardware knows that dread. Like watching your FLOPS budget just completely vanish on basic attention calculations.
Oh, it's brutal.
But before we even get into the MoE architecture and how they made it run that fast, we really need to look at the data because, a model's representational capacity doesn't actually matter if you don't have the data diversity to fill it.
Yeah, the fuel for the engine. And historically, robotics has been completely starved for data.
Right. Traditional policies usually just rely on small, super clean motion capture data sets.
Yeah, data sets like AMAS or LEFN1, and those are great. I mean, they give you beautifully clean, mathematically perfect kinematics. The problem is just volume.
You can't put a MoCap suit on a million random people.
Right. You can't capture people doing unpredictable, unstructured things out in the real world with optical markers. You end up with, a lot of walking, some running, basic reaching.
A lot of very sterile lab movements.
Exactly. You totally miss the infinite chaotic variations of actual human movement.
Which brings us to HoloMotion-1's solution. They basically abandoned the MoCap-only constraint and scaled up using what they call Motion Million.
Yeah, Motion Million.
It's a data set of over 2,000 hours of motion, but it's reconstructed directly from in-the-wild monocular videos. So they're pulling from videos to get that massive behavioral diversity. Everything from gymnastics to, someone stumbling on the street.
And if you work in 3D pose estimation, you already know this, relying on flat 2D video introduces a massive data engineering nightmare.
The reconstruction noise.
The noise is brutal. When you force software to extract 3D joint positions from a 2D YouTube clip, the data is just flooded with artifacts.
Because it's trying to guess depths from pixels.
Right.
So you end up with limbs clipping straight through torsos, or the center of mass is just jittering all over the place.
Yeah, or the lighting changes and the pose estimation totally freaks out. So if you just train a robot on that raw data, it's going to learn a deeply corrupted version of physics.
Okay, so how do they fix that? Because I'm picturing the robot just twitching and glitching out, trying to mimic a bad video render.
So they use a hybrid regime. They use the wild video data for the behavioral diversity, but they anchor it using high-fidelity supervision.
Anchoring it, meaning what? Like mixing in the MoCap?
Mixing in curated MoCap, plus a ton of in-house data they gathered using Piasu 4 VR headsets and Noitum inertial suits.
Oh, okay.
Those hardware tracking systems give you the ground truth you need to basically stabilize the noisy video estimate.
It kind of reminds me of training large language models right now. You scrape the absolute unfiltered chaos of Reddit to get a huge vocabulary and all those weird conversational edge cases.
All right.
But then you mix in perfectly edited encyclopedias and textbooks, so the model actually has factual grounding and grammar.
That's a perfect analogy. The internet video is Reddit, and the VR and MoCap data are the encyclopedias keeping the robot tied to physical reality.
Okay, but let me push back on that a bit, because the video data is still the vast majority of those 2,000 hours, right?
It is, yeah.
So if a video has a terrible compression glitch and like a guy's knee bends completely backward for 3 frames, why doesn't the neural net just memorize that? Won't the policy output a crazy torque spike trying to bend the robot's knee backward?
That exact fear is why the robotics field avoided video data for years. But the secret is how they handle the physics simulation during training.
Okay, walk me through that.
In Isaac Lab, the policy isn't just passively watching the kinematic data like a generative AI video model would. It actually has to output real joint torques to track the motion while constrained inside a rigid body physics simulator.
So the physics engine itself acts as a hard filter against impossible moves.
Exactly. If you try to bend a rigid robot joint backward in a simulator, it physically can't. Plus, they hammer the simulated robot with domain randomization.
Right. Changing the friction, the mass.
Yeah, randomizing the mass at the links, changing motor gains, and literally applying random physical pushes to the robot's base while it's trying to move.
But wait, any physics simulator has blind spots. If Isaac Lab's friction model isn't completely perfect, couldn't the policy learn some hyper-specific recovery trick that works in math but fails the second you put the real robot on a slick tile floor?
Yes, if they only rewarded pure tracking accuracy, it would massively overfit to the simulator's quirks, so they use heavy regularization.
Okay, what kind of penalties are we talking about?
They penalize extreme joint accelerations, rapid changes in action rates, and excessive torque.
So if it tries to copy that 3-frame knee glitch,
It would have to generate a massive, instantaneous torque spike. That violates the penalty, destabilizes the robot, and usually triggers a termination condition, like the robot's root height dropping too low.
so the episode just terminates. It gets a huge negative reward, and the network learns, okay, mimicking video glitches is a terrible strategy.
Precisely. The physics constraints and those penalties force the model to naturally smooth out the noise. It stops trying to copy the pixels and learns to extract the underlying physical intent of the motion.
That's brilliant, projecting noisy data onto a manifold of actual possible energy-efficient movements.
Right. But having all that beautiful physically filtered data brings up the next problem, capacity.
Right, because a standard MLP, a multi-layer perceptron, just doesn't have the sequence modeling chops to digest 2,000 hours of crazy temporal variance.
No, not even close. You need a transformer.
But we just established that dense transformers are way too slow for a 50 hertz control loop. If it takes 200 milliseconds to calculate attention, the robot is already on the floor.
Which is why the architecture is the second major pillar. They engineered a causal decoder-only transformer. And they used modern tricks, RMS norm, rotary positional embeddings, grouped query attention to save memory bandwidth. But the real magic is the MoE layer, the mixture of experts.
And the parameter counts here are just fascinating. The whole model is about 400 million parameters, right?
Yeah, 400 million total.
But it only activates around 7 million parameters per control step. So they have one shared expert and 1,024 fine experts. And the router only picks the top 2 fine experts per token.
That sparsity is everything. You get the representational memory of a massive 400 million parameter network, enough to memorize martial arts, slow walking, dynamic dancing, all from those 2,000 hours.
But on the robot's actual embedded compute chip,
You're only running the math for 7 million parameters.
yeah, it's such a clever design. And having that one shared expert alongside the fine experts, the shared one, activates on every single token, right?
Yep, every single time.
So it's basically forced to learn the universal rules of gravity and balance, like the core physics engine of keeping a bipedal robot upright.
Exactly. And then the 1,024 fine experts are specialized style modules. They kick in for specific edge cases, like a sudden jump or a sharp turn.
It's a really elegant division of labor, but how do you make sure the router makes smart decisions?
They apply auxiliary losses right before the MoE layer. So before the hidden representation goes to the router, prediction heads force the network to estimate base linear velocity, body contact states, and root relative positions.
Wait, so by forcing it to predict if its foot is touching the ground before routing?
You guarantee the early layers have explicitly encoded the physical geometry of the motion.
Right, because if it doesn't mathematically know its foot is in the air, it's going to apply the wrong torque anyway. So you're grounding the routing decision in rigorous physical reality.
It sets the rider up for success. And they also use a dead expert margin regularizer
To prevent expert collapse.
Yeah. Normally in MOE, the router gets lazy and just dumps all the tokens into the same 5 experts, leaving the other 1,000 completely dead. This regularizer dynamically penalizes the overused experts, forcing it to distribute the load.
Okay, but let's talk about the routing mechanism in the real world.
Yeah.
Because MOE routing can be incredibly volatile.
Oh, absolutely.
A tiny shift in the input vector can completely change which experts get activated. So imagine the physical robot is deployed. It experiences a microslip on a dusty floor that Isaac Lab didn't perfectly model. The robot's proprioceptive physical state changes instantly. Doesn't that noisy feedback cause the rider to totally panic, rapidly switch experts, and basically cause the robot to faceplant?
If they built it naively, yes. If they fed the noisy, real-time physical state of the robot into the router, the dynamic noise of the real world would trigger catastrophic routing oscillations.
So what did they do?
This is honestly one of the most elegant tricks in the paper. The router is conditioned exclusively on the reference motion, the goal state.
Wait, really?
Yeah, it is intentionally blind to the robot's proprioceptive state.
Oh, wow. So by decoupling the routing decision from the real-time physical feedback, they totally insulate the expert assignment from the sim-to-real gap.
Think about it. The reference motion, what you want the robot to do, is stable. The robot's actual physical state, its joint angles, its balance in the real world is noisy and unpredictable.
Right.
So by only showing the clean reference motion to the router, the choice of expert stays perfectly consistent. The dynamic noise is handled entirely by the experts themselves after they've been chosen.
You're splitting the cognitive load. The router just asks, what is the intent here? It sees a leaping motion and says, cool, activate the leaping expert.
Exactly.
And then those leaping experts look at the noisy, real-world data and figure out, okay, how do I actually execute this leap right now without falling? That is brilliant. You get MOE capacity without the routing fragility.
It's a phenomenal solution, but having this amazing architecture doesn't mean anything if you literally can't compute the gradients to train it.
The training bottleneck.
Right. They're optimizing this autoregressive transformer using PPO, proximal policy optimization, across 8,192 parallel environments simultaneously.
Which is just a staggering amount of compute.
Standard step-level PPO is fundamentally inefficient for causal sequence models. Because normally you roll out your trajectories and then you shuffle the individual time steps randomly into mini batches.
Yeah, to break the temporal correlation. That's standard RL practice.
But HoloMotion-1 is a causal transformer. It has a context window, let's call it length C. Because of how autoregressive models work, every time you evaluate a single shuffled time step, you have to recompute the entire overlapping observation prefix that came before it.
So if my context window is 32 tokens long, and I want to calculate the action for step 32, I have to compute steps 1 through 31.
Right. And if the very next random sample in your batch happens to be step 31 from a different sequence, you have to recompute steps 1 through 30 all over again.
Oh my God. You're doing OC, redundant recomputation, for every single step.
Yes. When you scale that to thousands of hours of data across 8,000 parallel environments, that redundant math completely saturates your GPUs. It becomes totally intractable to train unless you have an infinite budget.
So this is where sequence-level PPO comes in. And it's, okay, think about standard PPO like trying to binge watch a serialized TV show, but you're picking random 1-minute clips out of a hat. And for every random clip you pull, you're forced to read the Wikipedia summary of the previous 30 minutes, just so you have the context to understand that 1 minute.
Yeah.
It's a maddening waste of time.
It really is.
So sequence-level PPO is just hitting play.
Hitting play. You preserve the contiguous rollout segments. Instead of shuffling the time steps, you feed them into the transformer chronologically.
And that leverages the autoregressive nature of the model.
Exactly. A single batched forward pass computes the action log probabilities for all the time steps in the sequence at the same time. You completely eliminate the overlapping prefix recomputation.
And the performance gains here are just wild. They achieved a 22 times speed up in training throughput compared to the baseline sliding window PPO.
22 times.
That's the difference between waiting a month for a training run to finish versus getting it done in a day and a half. For an ML engineer, that completely changes your iteration speed. You can actually tune hyperparameters.
And they took that same optimization philosophy into deployment. They use a KB cache implemented as a ring buffer for inference.
Oh, nice. because memory fragmentation on embedded chips will totally kill your loop speed.
Exactly. Dynamic allocation latency is a nightmare. With a pre-allocated ring buffer, as new tokens come in, they just overwrite the oldest token circularly.
Zero memory allocation overhead.
Zero. The model only processes the newly observed token while attending to the cached context. It drops the inference attention complexity from OC squared down to OC.
Which gives them an 11 times speed up on inference. They're hitting 200 to 300 hertz execution speeds directly on board the hardware, so the 50 hertz constraint is suddenly breathing easy.
Right. It proves that running large-scale transformer RL on edge hardware isn't just theoretical anymore.
But, all this math, the MoMoE, the sequence-level PPO, it only matters if the robot actually works.
Time for physical deployment.
Right. They put HoloMotion-1 onto the physical Unitree G1 humanoid, and their pipeline for this is super rigorous.
Yeah, they structured all the motion data using HDF5 databases. Which sounds boring, but if you stream 2,000 hours of high-dimensional data naively, your CPU I/O will totally bottleneck your GPUs.
So HDF5 lets them do chunked, batched loading straight into VRAM.
Yep. They train in Isaac Lab, do offline evals in MuJoCo to make sure the physics generalize across engines, and then package it in a ROS2 runtime for the real world.
And the zero-shot generalization they tested is amazing.
Yeah.
They ran it on totally unseen datasets, Momo, HumanAct 12, Twist 2 for VR Teleup, and even TikTok Dance.
Mm-hmm.
And against the strongest baseline, which was Sonic, they got a 40% lower mean per key point position error.
And MPKTE is the metric that matters here. It measures the global positional deviation of all the robot's physical links compared to the reference motion in millimeters. Dropping that by 40% zero shot is a generational leap.
And the success rate metric, over 97.5% success zero shot. And success means the robot's root height stayed within a quarter of a meter of the target without falling.
Which is incredible when you consider they're tracking highly dynamic TikTok dances and contact-rich kung fu crawls.
Yeah, a human doing a TikTok dance has these crazy, rapid center of mass shifts that standard lab MoCap just doesn't teach you.
Which perfectly validates their hybrid data thesis. Feeding it the raw chaos of internet video gave the model a deep, generalized understanding of momentum and balance. It didn't memorize poses. It learned how mass moves through space.
Without any task-specific fine-tuning, it just translates 2D pixel space dances into safe torques for a 29-degree of freedom machine.
So looking at what this achieves today, we have to look at the roadmap Horizon Robotics laid out. They call it the 4NE roadmap.
Okay, 4NE.
HoloMotion-1 solves stage 1, which is imitate any pose. Stage 2 is follow any command, translating language instructions or partial VR inputs into full body motion.
Makes sense.
Stage 3 is move on any terrain, using depth sensing to navigate stairs and slopes. And stage 4 is the big one. Control any embodiment.
Okay, this brings up a really provocative thought for you to chew on. We talked about how the pre-MoE layers force the network to encode this universal geometry of motion, right?
Right.
And the router is completely blind to the physical hardware state. So the network is basically separating the pure intent of a motion from the hardware that executes it. If that representation of intent really is universal, how far away are we from a single foundation model where you just swap out the final action decoder and the same brain can control a bipedal robot, a quadruped dog, and an industrial robot arm at the same time?
If the core model understands physics independently of the hardware,
Yeah.
the embodiment just becomes a peripheral device.
Exactly. You're building a universal physics brain that can pilot literally any chassis you plug it into. And if the robot chassis is just a peripheral monitor for an AI brain, what happens to the entire hardware-specific robotics engineering industry?
It completely upends it.
If HoloMotion-1 is the first draft of this physical encyclopedia, we might be looking at the end of bespoke hardware control entirely, something to mull over. Thanks for joining us on AI Paper Slop.